The Materials World modules are hands-on, inquiry and design-based curriculum units for middle and high school students. Using principles from the interdisciplinary fields of materials science and nanotechnology, this curriculum aligns well with STEM objectives, engages students, and adds relevance to existing curriculum.
As a high school chemistry teacher, one of the Material World's modules that I use in my curriculum is polymers. What I particularly like about the polymer unit is that it helps students make the connections between the structure of molecules and their properties. This is so much a part of the National Science Standards, physical science standards. In addition, the polymers and the other modules help students integrate the technology standard or inquiry by design into a middle school or high school curriculum. I put it into my curriculum after a unit on bonding where students have learned about polarity, but it also can be placed obviously into a unit on organic chemistry. All of the activities that students do within the module prepare them to do the design project, which is to create a new application or a hopeful improvement on an existing application for a polymer. The first activity is called Changing Polymer Pellets, and it's the hook to kind of pique students' interest in polymers. They experiment with a polymer that's a soil additive called Soil Moist, and they're asked to make predictions on how many times or how much water Soil Moist can absorb. And after a little bit of water in 15 or so minutes, Soil Moist does absorb about 200 times its mass in water. This gets students to learn about cross-linked polymers and the fact that when the polymer chains are bonded across the chains, they allow the polymer to act like a sponge. But what's really nice, what you observe happening in the classroom, is students ask further questions. The teachers love to hear, like, what would happen if we use distilled water instead of tap water, or what would happen if we let this sit overnight? And it's always good to encourage students to pursue those questions. Although one question you probably don't want them to pursue is what would happen if you put the Soil Moist pellets in the sink, because that gets to be a little bit messier than most people want to cope with. The second activity is the Polymer Hunt, which gets students to realize that polymers are really all around them. And this can be done as a classroom activity or as a homework assignment. Sometimes I've asked students to bring in samples of polymers, and we get a wide array of things that students do find to bring in. Often students are aware of recycling codes. So one place they look for polymers is in their recycling bin, and it's a perfect time to talk about what those different numbers mean in terms of the types of polymers, and to then again start to say, well, what are the differences in properties given the different structures? Often differences come up also between natural and synthetic polymers. Most synthetic polymers are some variation on a plastic, but leather and many kinds of foods are examples of natural polymers. In Activity 3, students learn about the property of viscosity, or resistance to flow. In the first part, they're given vials with materials with different molecular weights, and they compare their viscosity by timing how long it takes for a bubble to go from one part of the tube to the other end. And in this, they see that the substance that has a higher molecular weight takes longer for the bubble to travel, so that the higher the molecular weight, the greater the viscosity. This is explained to students by using an analogy of a bowl of spaghetti, where the longer the noodles are, the more tangled up they get, and the more difficult they are to separate, or more viscous they'd be, as opposed to a bowl of shorter noodles, which would be more easily separated. It also gets students to think back to the materials that they brought in during their polymer hunt, where they now can kind of realize that most of their polymers weren't liquids, but solids. So most of the polymers in our everyday life are very long molecules with very high viscosities that in fact make them exist as a solid state. The second part of the activity has two goals. The first is for students to continue to see the relationship between concentration, between molecular weight and now also concentration and viscosity by comparing the spreadability of different lengths of a polymer and different concentrations. As they spread the polymer on a slide using a pipette, they see that the longer the molecular weight, the more difficult it is to spread. And in addition, the second goal is this process is a skill known as casting, which is one of the common ways polymers are applied to surfaces, and one way that students may be applying polymers to surfaces in their design project. For example, a student may choose to apply a polymer to a baseball to try and make it waterproof. In Activity 4, students test the strength of different polymer films. They cast slides of 3 different molecular weights of one polymer, polyvinyl acetate, and let those slides dry to form polymer films. This usually takes a day or two, so often I have students do this at the end of Activity 3 after they've had some practice in the skill of casting. After the films are dried, they're removed from the slides and hung between 2 clips on a ring stand with a weight suspended from the bottom. By measuring the length of the polymer film over different periods of time, students see the relationship between molecular weight and tensile strength specifically. And the longer the molecular weight, the greater the tensile strength, because the less stretch there is in the film. Activity 5 is the key activity in the module. In this one, students see the relationship between different polymers and their ability to absorb water. Slides or watch glasses of 3 different polymers are casted: polyvinyl alcohol, polyvinyl acetate, and polystyrene, allowed to dry and then soaked in water for a period of time. The masses before the soaking in water and after are compared, and what students see is that the polar polyvinyl alcohol totally dissolves in water, whereas the nonpolar polystyrene doesn't absorb anything. And this is usually where students start in their thinking as they begin to plan their design. The design experiment is the culminating activity in the module, and the module provides for 2 types of designs. One is more structured, where the students as a class design an optimal humidity sensor by dissolving some cobalt chloride in a polymer solution. But with my classes, I do the unstructured design project, where students get to design an application of any type of polymer or any polymer application that they choose. In the past, I've had students trying to improve upon hairspray, and they bring in their Barbie dolls and cut the hair to the same length and spray the polymer on their Barbies. They've tried to make a better roach motel, tried to make nylons more run-proof, and tried to waterproof just about everything that you could think of waterproofing. This is really challenging for students, especially coming up with the question and then figuring out what data do I collect to allow me to decide which is the best prototype for my design. But at the end of the year, when I have students reflect on their year of chemistry, most say that this is one of the more significant things that they've done, even though it is a challenge.